We're going to go ahead and get started here. So Tom Grubb is a 36-year NASA civil servant and the AR/VR product development lead for the NASA Goddard Space Flight Center AR/VR Research and Development Lab, which is developing multiple augmented and virtual reality prototypes and projects in support of science and engineering, including the Roman Space Telescope, CCRS, and the on-orbit servicing, assembly, and manufacturing missions. He is the project lead for the Mixed Reality Exploration Toolkit, also known as MERIT, and a NASA open source XR tool for rapidly building XR environments for NASA domain problems. He is the principal investigator on the Earth Science Technology Office Project Geovisualization and
It's a long, just say Velixer.
For Velixer for which seeks to visualize climate model data in XR. So please welcome to the stage, Tom Grubb.
Thank you. And this is...
Yeah.
Okay. All right, welcome. I'm Tom Grubb. So yes, I'll be basically talking about Velixer. This was funded through the NASA Earth Science Technology Office, and let's just get into it. It's our team, it's NASA, a bunch of universities, College Park with Roger and Matthias Zwicker, and all the graduate interns, University of Maryland, Baltimore County with Don, who's cheering in the back, and University of North Texas. So background. So the way that the scientists look at climate models is they basically grid up the Earth. They'll take the Earth and say, okay, at this location and at this time, what's the wind speed? What's the temperature? Whatever. This is during a climate model run. And then you go to the next step in the climate model run, and at that same grid, what's the wind speed, what's the temperature? And even though visually and we understand that this cloud and this grid is moving this way, the climate models don't know that. It's all gridded up. So it can be difficult to take that data and to understand stuff because it's not evolving the way they want. It can be difficult to identify, track, understand these features. And then when you get them in a 2D screen, it gets worse. This is inherently 3D data, and you're seeing it on the 2D screen. And all of the phenomena they want to look at in the atmosphere is very 3D, it's very flow-oriented, et cetera. So that's where we came from. And then we said, hey, we can apply all these great benefits from XR, that it helps you understand the complex relationships, spatially related relationships. You can use your binocular vision to see, and easily look at things, improving the interactions, just a simple thing like, let me point at this place above the North Pole. On a flat computer screen, you got to get the X, Y, Y, Z, X, Z, and match everything else up, but you just go like this in 3D space. And then, of course, there's the collaboration that was actually mentioned earlier. We wanted to combine that and combine the XR with the Lagrangian models. I kind of skipped through that. So instead of Eulerian gridded data, we want to have data that follows through time. So instead of going from one grid to the next, we want the models to output a particle that travels from the smoke from a fire in Canada as it goes up into the atmosphere, goes through the tropopause, into the stratosphere, and across the globe. And use that to allow the scientists to understand the data as well as interact with the data to help with subsequent climate model runs. And we didn't want to just graft it on. We wanted to make this a true tool that the scientists could use. So we came up with Velixer. and I'll ignore, I'm like Blake, I don't want to say out the whole thing. The whole point is that we added a trajectory model to follow those particles into a climate model called GEOS, the Goddard Earth Observing System. So this is one of those models that if you go out to weather.com and you look at the weather, these models generate that type of data. Add a trajectory model and then have it output a file that contains an animated point cloud. So all the points that you want to follow in the simulation through time. And then pull that into XR and allow the scientists to interact with that. And I should state, this is, this ESTO project, we started in, even though the date was for 2021, we started really 2022, and we're finishing up this calendar year. So help the scientists understand phenomena, interact with it in an immersive way, and help them do like what-if investigations. And we believe that there's a few advancements we're going to bring to the table. One, just adding a trajectory model to these climate models, we've found that the scientists think this is an advance. This is something they want. There are limitations. This is an atmospheric trajectory model, and it doesn't do too well below I forget what it's called, planetary boundary layer? I'm forgetting now. Too close to the ground, it's too chaotic. You need to do like statistical methods, et cetera. But once it starts getting above that area, it's actually very accurate. And then we are adding all of this into our mixed reality exploration toolkit, Merit, and this will be all open source. We had two use cases from the scientists. One is the wildfires that I already mentioned, following those the smoke plumes as they go and evolve throughout over the world. And another is a very similar thing where energetic thunderstorms can take pollution, which is usually lower, closer to the ground. Those thunderstorms can suck up the pollution and actually punch it through the tropopause again and across the globe. So we have two scientists, and they're both working, hoping to use this. So what have we been doing? We had we're doing a 2-year phase development. There was a foundation phase where we did requirements, a little bit of high-level design. What we found is that it's very easy for programmers and scientists to talk past each other. I don't understand their frame of reference, and they don't understand mine, and I would think they understand me, and it was wrong. Human factors, we have a human factors group. The University of North Texas is our human factors group. They helped tremendously. They sat down with the scientists, tried to understand the steps they do, the cognitive model, how they thought about the data, how they thought about what they wanted to do next, what tools, et cetera, and that helped a lot. That said, we still didn't understand each other, and we had massive requirements creep, which is good and bad. We want to make a tool they can actually use, but that turned out to be a lot more work than we initially hoped or got funded for. So we're working on that. And then we went into development phase, and that's basically been over a year. And right at this point, we're kind of doing a rapid refinement phase. Get a release out, have people use it, talk about what's wrong with it, and refine on that. I mentioned GEOS earlier. It's just briefly, it's this gridded climate model. It's been used a long time. It's not as accurate as the models you will see for the weather, but it's much better in that it holds a lot more stuff. It carries around a lot more data that the scientists are interested in to answer science questions beyond what's, is it going to rain, later or whatever. And so then GigaTrash, which was the trajectory model, was integrated into it. GigaTrash was originally developed at Goddard. They are going through the whole open source license. They hadn't bothered before that, but now they're going through the open source license, and they're pulling it in as a model, and it can do some amazing things with particles in a kinematic, isentropic, and diabatic. And don't ask me really what those mean. I don't know. Point clouds was a big part of this. We're going to pull in point clouds. And we have competing requirements. Felixer, it turns out the scientists don't need a lot of particles. It's, in the tens of thousands animated, which if you think animated, you take tens of thousands and times it by 1,000 frames or however many, it becomes a lot fast. But it's a lot more manageable than billions of points that you need for other applications. But since we're pulling this into our open source solution Merit, we need to balance these. So we've been throwing a lot of different technologies at the wall, trying out different things. We looked at a open source package called Compute Rasterizer. It can handle billions of points. It could animate, but it doesn't integrate with Unity. And we've had a lot of problems with trying to pull that in directly. However, we're using it for other purposes, which I'll mention later. We tried, well, what if we run that point clouds renderer on a remote system and use that to then pull in? And that did not look right because it needs to actually integrate with other parts that are not being rendered out there. Then we've done a custom solution that's going to work for what we need. The Unity, we're using the Unity shader language. It can handle millions of points and animate those. We've also pulled in open source Poetry, which can handle billions of points but can't animate them. It's good, it does the whole partitioning of data so it can optimize and everything else. And we think this would be useful for other use cases, just not Felixer. And then we have this part of this project, which I haven't touched on yet, and it's coming out of Maryland, is we want to use the neural net machine learning to optimize, and specifically for super resolution. So it's going to take all the great features you're seeing with stable diffusion and all those, filling in gaps or aliasing or anything else, and bringing it to our specific science use case. We've been using that little box, white box, training data. So the compute rasterizer, the one we can't integrate, we've been using it to train this neural net to do super resolution. So it's got, it's got the particles at the full resolution, flow fields, and then the idea being that we can animate a smaller subset of the particles, like on the left, and use the neural net to fill in the gaps and make it look better. And this is obviously optional. Scientists don't really like made-up data, but it can help them understand it first, and then let me dive into the real data. So, here's an example. CR is a compute rasterizer version. This is with the more lower resolution of the points, and then using the neural net to upgrade it, whether it's 1x, 2x, or 10x. And at 2x, it's probably good. Probably 4x. 10x is getting a little bit blurry kind of looking and not as detailed. I probably should have had this slide earlier. We're building off in the XR domain tool developed at Goddard called Merit. We've been developing it since, I believe, 2018. It's NASA open source, and you can get it. We try to have a release every year. It can be difficult sometimes. But the whole idea of Merit is that instead of having the user have to have Unity to customize it, we want them to customize it through XML files that describe your domain. Oh, I'm in this 3D model of this room, and I want this podium, and I want this drawing, and this type of thing. And we primarily target VR. We have a desktop mode for people who don't have the hardware. And then HoloLens 2 is the last one, though we usually lag behind with that. And we're in Unity and C#. So we put it all together, and our concept was like, hey, let's make it so, like just as a kid, when you play D&D or something and you have this relief map and table, let's have a table or a globe in the virtual room that's full of the different science data and is full of these different layers so they can get the context. Not just the animated particles, but let's bring in the DEM data from Bing. Let's bring in state boundaries. Let's bring in GOES data, which is cloud data, or NextRad data. Put them all together and allow the scientists to animate the point clouds and work with them. And you know, we have the tropopause, which also comes from the climate model. You can start controlling things, the opacity, et cetera. Here, the flow lines and the tropopause is the wavy thing underneath it. The flow lines from the particles, and you can animate through them. You can select the particles. I mentioned that it's kind of a round trip. So they will do a climate simulation, get all these particles, and if you have a fire, some of those smoke particles are just going to trail away, and they're not going to be interesting. They didn't go up into the stratosphere and across the globe. So you need to say, oh no, these particles are the ones that should be our initial use cases for subsequent runs. And here we have, here's an example of requirements creep. They were like, well, that's great with the point clouds, but we want volumetrics. We want isosurfaces. We want all this stuff. We want a cut plane. And we were like, oh God. So we had to add all of that. And I'm making one of my interns miserable this summer implementing features. He shouldn't be here. He should be working. Get back to work. So that idea of a holographic table that we could all get around and that they can see and zoom into the area they want, see all the contextual data around it, you know, move forwards and backwards in time, you know, layer all these data. We have the 3D layers, the animated point clouds, the volumetrics, and we're getting a lot of the data through, you know, different OGC standards, you know, the web mapping services, et cetera. We're now looking at 3D tiles is another OGC standard, and then, you know, some NOAA standards and all. And of course, in the interest of time, we're supporting the features of the standards that we need right now, and we know work with our data sources. But we'll build that out as we go along. I mentioned the human factors. They were really helpful in helping us understand the scientists in the beginning. They are helpful as we iterate on with the scientists. And they actually developed a GAZE application that can be executed outside of Merit or any application. And we'll add that whole, you know, what are they looking at, and et cetera, and output a CSV file to help you track. So you don't actually have to embed that inside the application. It can be done outside of it. So conclusion. Well, atmospheric phenomena, the world isn't divided up into grids. You need to understand it as it flows and moves, and the scientists need to understand it that way. We believe that gives them a better comprehension of the processes if they can follow it in that natural way. Integrating the trajectory model with GEOS is going to have benefits beyond Velixer. We think that, you know, leveraging Merit and adding all these features is just going to, it has a lot of applicability. I put Earth science, but it's beyond that. We've already put in 2 proposals to use the Velixer technology for lunar. Swap out the layers that are on the Earth, let's put it on the moon. An astrophysicist wants to do, instead of let's get through the layers of the atmosphere, let's take an alien sun and layer down and go through its, so looking at it down. So we believe it has a lot of potential to going forward. And by taking the XR and very loosely coupling it through this point clouds file, we can do this. We can do these different domains, and we can even position Velixer for a whole series of, well, they're going beyond climate models, and they're going into this idea of the earth science digital twin, where just like you have a digital twin for a mechanical thing that describes the entire mechanical thing and how it will behave, they want to do it for the Earth. And we think by Velixer, by this loosely coupling it, using standards, we can position it to be a front end on those Earth science digital twins. And that's it. Questions? Sure.
So, so you mentioned moving, you were able to move from the Earth to the moon by changing just some of the textures, right?
Well,
so
the layerings.
The layerings. So is your Earth model, your globe model, is it spherical or is it the more oblate orb shaped of the Earth?
So we designed it that there's kind of an overriding like layer manager, and it says to the layers, here's the projection. And it needs to figure out how to do it for the projection. And right now we have a globular projection, and there's a specific name for it, I don't remember. And then the flat projection and a wall projection, but we can easily add others. And in fact, by having those globe and the flat projection, that's quickly teasing out bugs that, oh, I have the shader, it works beautiful flat, but as soon as it did this, globular, it looks like a monster. So we did something wrong. So, and there's functions on the table to say, at this position, you need to do this pixel type thing. So in theory, whatever projection we put in, the layers, should be able to handle with that, conversion.
Hi.
Yeah.
I noticed in the point clouds, when you're modeling the particles from smoke, for example, you're using two different colors for that visualization. Is that because you're modeling two different particle types interacting with one another, or is that just to help visualize all of them together as they move around the Earth?
It can depend. So we allow a few things. Like when you select, we can say, okay, let's put it into basically a set, a point cloud set, and we can have those colored is one thing. If you notice the volumetric, which was red and blue as well, apparently, I think red is rising data and blue is data that, the wind's going lower in the pressure and altitude. We allow them to assign a color map, and the scientists have very much, this is the type of color map I like to use for this data. So it's going to be what the scientists think.
All right, thank you.
We will be doing demos at 3 to 5 in the room, so you can try it out. As I mentioned, we're iterating on it, so there are some rough patches, but it truly is, I'm very proud of this project and what we can do and what our developers and interns have been able to do. Thank you very much.